Hello everyone, welcome to this lecture which covers the computer-aided solutions for asset-based systems. So basically in this lecture we're going to develop a Microsoft Excel spreadsheet to either calculate the solution pH or to construct the PC pH diagram, similar to what we did, for example, in the previous lecture on graphical solutions. And then later on, we're going to use MINTEQ, Visual MINTEQ, to solve for both solution pH and also constructing the PC pH diagram. So this is the third lecture on how we can basically calculate the solution pH, or in general, speciation for acid-base systems. So the first lecture in this series, we talked about algebra, using algebra, following by some assumption that we can eventually simplify the equations to preferably a linear equation, and then solve that equation using basically the same basic algebra. And the second lecture in the series, we talked about graphical solution, basically constructing graphs with some logics behind it, following some rules, and eventually calculate for speciation and the solution pH. So here in this lecture, we're going to use computers in order to solve for speciation. So this is again another tool that we can implement for a wide range of environmental applications, specifically those that deal with asset-based systems. So basically the pipeline that we talked about in the previous two lectures was something like a three-step process. So in step one, this was all about identifying species, or we define that as like the N species. Then in step two, we basically develop N equations. And in step three, we basically solve. So the way we solve this equation in the first lecture was basically using algebra. In the second lecture, we use graphs. And in this lecture, we're using computer or computer softwares to either solve or basically to integrate all the pipelines in order to have a speciation at the end. So for example, something that is happening in Visual MINTEQ. So specifically, the two software or the two approaches that we're taking in this lecture is either using Microsoft Excel, the spreadsheet Microsoft Excel, or to use this open source software with a huge thermodynamic database. It's called Visual MINTEQ, which can be installed and downloaded easily. So these are basically a powerful tool for like a wide range of application within environmental chemistry framework. But here in this particular lecture, we're focusing on only asset-based system in order to get the speciation. So we start with the Microsoft Excel approach. So basically using Excel for two specific applications. So first using Excel to solve a pH of a weak acid using a spreadsheet, which are basically example 1 and 2, or construct a PC pH diagram, which will be covered in example 3. So two goals in we're pursuing using Microsoft Excel. So the first example is basically similar, it's basically the same as what we talked about in the past two lectures, but we took different approaches to solve this system. The first lecture we talked about algebra, the second lecture we talked about graphs, But here we want to develop a Microsoft Excel in order to find a solution pH when 10 to the minus 3 molar propionic acid is added to water. And we know the value for pKa. And our job would be basically to estimate the pH. So to just refresh your mind, this was a monoprotic acid that was dissociated to PR minus plus H plus, and then we had this Ka value representing the ratio of activity, but here, for the sake of simplicity, we use the ratio of concentration. For any aquatic system, we also have water, so we're also dealing with this Kw, which representing the ratio of the contributions of proton and hydroxide in the system. The total mass balance was for PR, and the system is basically concentration of HPR plus the concentration of PR minus. So we're going to use Excel to find for solution pH. As the first example, we're trying to calculate the solution pH when a weak acid is added to pure water. So basically, a solution of 10 to the minus 3 molar propionic acid, noted as HPR, is added to water, and our job is to basically calculate the solution pH. So I designed this spreadsheet that you can use for your homework or for your future applications. So basically, here we need to enter the chemical that is added to pure water, in this case HPR. And then the total concentration was 10 to the minus 3. And then the total PR concentration would be basically is equal, in every 1 mole of HPR, we have 1 mole of PR. So the total mole of PR would be equal to the concentration. So this would be equal to the concentration. So the next part, I'm here showing the reactions that are going to happen. The first one is basically water dissociation, as we talked about before. We have it all the time, and we have the K value. This is assumed to be at room temperature, so the K value for water dissociation would be 10 to the minus 14. And then we have this acid dissociation, HPR going to PR minus and H plus, and the pKa value is given as 4.87. But as you saw in most of the calculation, we actually prefer a Ka, so that's it's basically 10 to the minus the value of pKa. And the second part, after figuring out about the total concentration and the reaction, all the possible reactions. So here, this is basically the only possibilities for reaction that might happen in the solution. Then our job is to figure out about the speciation. So the species that we have is H plus and OH minus that is coming from water. And also we have HPR and PR minus that is introduced because of the addition of propionic acid. We have also the charge balance for this Microsoft spreadsheet technique. Charge balance is actually the core. So writing the charge balance, that means that the concentration of the positively charged, which in this case is only H plus, is equal to the concentration of all the negative charge, in this case including OH minus plus PR minus as well. So this is basically our simple charge balance equation. And then we introduced this alpha term in the first lecture of acid base. So basically it's a notation system that we use in order to somehow simplify the calculation. So we're dealing with a monoprotic acid. So basically we only have alpha 0 and alpha 1. We drove this relationship before, but here we summarize it here as well. Alpha 0 is equal to the
concentration of proton divided by this term, and alpha 1 is the Ka value that we already have divided by this denominator, which is the same for alpha 0 and alpha 1. And we talked about this in class, that alpha 1 plus alpha 0 for monoprotic acid is equal to 1. And alpha 0 is basically defined as the HPR concentration, or protonated species concentration, divided by the total concentration. So basically this is a fraction of dissociation, basically this alpha term. And alpha 1 is obviously PR divided by the total amount of PR. And the total amount of PR is basically, in this case, is either in the form of HPR or in the form of PR minus. So the core logic behind this Excel spreadsheet is basically guessing the pH, and based on that doing the calculation, and then check whether charge balance is satisfied or not. So in this case, let's assume our guess is 0. So the concentration of proton would be 10 to the minus the pH. And based on the Kw term, we know that if we know the concentration of proton, we can calculate the concentration of OH minus. So that means Kw. But be careful, because it's not a variable. So we put this $2 one behind the letter, one behind the number, to keep this cell constant for all the table. This would be divided by the concentration of proton, which is a variable. So then it gives us the values for OH minus. Then the alpha 0 term, we define that to be the concentration of proton divided by this denominator, which is basically the concentration of proton, which is the variable, plus this constant, which is Ka, this term, again, because this is a constant, so we need to put this dollar sign, just the language that Excel uses to keep a constant rather than a variable that varies throughout the table. So we have this alpha 0 term, and then we have this alpha 1 term as well. So following the same thing here, basically Ka, again, it's a constant divided by denominator. Make sure you use this parentheses. So H plus again the constant, but we use this dollar sign, close parentheses. So as I mentioned briefly, alpha 0 plus alpha 1 must be equal to 1. And I defined this control term, very simple strategy to make sure that step by step our calculations are correct. So here I'm defining this control to be equal to alpha 0 plus alpha 1. And this has to be 0. And if I expand it for the whole table, this would be all equal to 0. So just a strategy to make sure that we are doing fine in terms of the calculation. So then, after having alpha values and also the total value, considering these two equations, I can calculate the concentration of HPR and PR minus. So HPR would be alpha 0 as a variable times the total concentration of PR, but this time this is a constant, so using the dollar. And then this PR minus would be basically alpha 1 value times the total concentration, but dollar sign. You can also define another control function here to make sure that HPR plus PR minus is also equal to total PR, but because we already have for alpha, and as long as you don't have like a calculate error in putting this constant value or this $2 sign, you should be fine. So now this is the last step, where the core of this Microsoft Excel strategy to calculate pH. So we know that at all of this given pH, we have the contribution, the speciation. But which one of this satisfy the charge balance? So by satisfying the charge balance, if we look back into the graphical solution, what we defined was that the left hand side of the charge balance, in this case H plus the concentration, must be equal to the right hand side. In this case OH minus plus PR minus. And then our strategy in graphical solution was basically where these two lines, the first line H plus, the second line OH minus plus PR minus would cross. So that would be our pH, or that point is the point that satisfies charge balance. So here, ideally, if we have the point that satisfies charge balance, if we subtract the concentration of negatively charged from the positively charged, so basically rearranging this equation in a way that everything goes to the left side, so H plus minus OH minus minus PR minus must be 0 if at that point of pH, so that would be the pH that satisfy the charge balance. So let's do this. So this would be H plus minus OH minus minus PR minus. So H plus minus OH minus minus PR minus. So if we do this, we see that the charge balance is around 1 here, then it's 1, then it's actually going down, and at some point it goes to negative. So we are looking for a point that charge balance is satisfied, or charge balance, or this term that we define. This is not necessarily the charge balance term. This is a term that we define based on charge balance. Similar term that LHS or RHS, right hand side or left hand side of the charge balance. This time the term that we defined was basically left hand side minus the right hand side, and that must be equal to 0. So here, because of the resolution, we cannot find the point because none of these values increasing by a unit of 1 is satisfying that. We're getting closer to that, but not satisfying, not equal to 0. But what we know here is this term here is positive up to here, and then it goes to negative. So that means this term driven based on charge balance, which is LHS minus RHS, is equal to 0 somewhere between 3 and 4. So that's the big information here. So in order to have a better understanding of finding a higher resolution, so here you can just say, oh, that's pH is between 3 and 4, but you don't know what's the more accurate number with, for example, 1 decimal. So what we can do is basically doing the same sort of calculation, but this time focusing on pH values between 3 and 4, but with a higher resolution. So I'm defining my pH as 3, then 3.05, so increasing the resolution, and then increasing by 0.05. So 3.05, 3.1, 3.15. So I have a high resolution, and I go between 3 and 4 because I know somewhere in this range I have my term closer to 0. So I'm increasing the resolution of my calculation. So this table is telling me is somewhere between 3 and 4. But now we need to basically do the same calculation as we did for here, like doing the same sort of calculation for this graph. Okay, this is, so we probably need to do it a little bit manual. So So here, if we look at this table, we see that all of them are positive, but then it changes to negative. So somewhere between 3.95 and 4, the charge balance, or the term that was defined based on charge balance, which must be equal to 0, will be satisfied. So the pH would be between 3.95 to 4. So here what we found was pH is between 3 and 4, but here is between 3.95 and 4. So the resolution is way higher compared to the first table. So depending on the type, the resolution that you want to find your pH, you can actually this time in the third table go from 3.95 to 4, but increasing with, for example, 0.01 unit. So you have like basically 5 rows. In that case, you have a better resolution of where the pH is. But for now, I think 2 decimals, I think is pretty accurate. So 3 point somewhere between 3.95 and 4 is where we have our pH for this given solution. And as you remember, we did the same example on algebraic solution and graphical solution lectures, and we figure out the pH, the exact pH is 3.96. So it's relatively simple. Excel spreadsheet would also give us the same number, but using a different twist that we used here to calculate the pH. So that's about the example 1 of the lecture.
So the second example is asking us the pretty much the same as the first example, but here instead of adding HPR, we added the salt of weak acid or the salt of propionic acid, which is in this case it's Na, the sodium salt. So instead of HPR, we added the same concentration of NaPr. So now our job would be to estimate the pH for the solution. So the reaction would be the same as basically the first example. So we basically have all of these species with all of these chemical reactions. So nothing changed from that perspective. But the only thing that is changing is the speciation. So basically, if we look at species, in addition to what we had before, so H plus, OH minus, HPR, and PR minus, this time we also have sodium ions. That's the biggest difference between here and the previous example. So our job would be developing a Microsoft spreadsheet in order to calculate for the solution pH when we have all of these species and see how the pH is different than the previous case when we added only HPR.
So on example 2, there's a minor difference, and that's that we're adding a salt of a weak acid, not the weak acid itself. So in the previous case, we added 10 to the minus 3 molar of HPR, and it resulted in a solution pH of 3.95. But now, this time, we're adding a salt of weak acid. So a salt of weak acid, in this case, sodium salt of that HPR, or that propionic acid. So basically, we're adding 10 to the minus 3 sodium NaPr. So the chemical that adds it is NaPr, basically the same concentration, 10 to the minus 3. And we know 1 mole of NaPr contains 1 mole of PR and 1 mole of sodium. So the concentration of total PR and total sodium would be the same as the initial concentration of the molecule. In terms of the reaction, it's basically the same as the previous reaction. So the sodium is not, we're assuming that it's not participating in any other reaction. So basically what we have is dissociation of this acid, HPR, and water as always. So this would be 1e to the minus 14. And this pKa was 4.87. So this one would be 10 to the minus the pKa. So this time the species are a bit different compared to the previous case. In the previous case, we had H plus as the only positively charged, but this time we have also sodium. And in terms of the negatively charged species, we have the same as the previous case, HPR, OH minus, and PR minus. And we also have HPR as our species. So basically, instead of 4, we have 5. That sodium concentration is added for this solution, in this solution. Therefore, sodium is a positively charged species, so it's a part of charge balance equation. So this would be the charge balance. Not sure why this was misspelled. So the charge balance this time would be all the positively charged species. The concentration is equal to all the negatively charged species. OH minus plus PR minus. So the alpha values would be the same because alphas are representing acid-base reaction, and this addition of sodium and this solution matrix doesn't impact the alpha terms. So it impacted the species, and also most importantly, it impacted the charge balance equation. So we're going to do the same as the previous case. So this time, sodium is not impacted by pH. So basically, sodium is not reacting in any acid-base reaction. So basically, at any pH, the concentration of sodium would be basically the same as the total concentration. So it's not changing. It's the only species of sodium. So this would stay the same at any given pH. So this is the biggest difference between example 1 and example 2. So developing the term for charge balance, so H plus sodium. This is the left hand side minus the negative charge. This would be OH minus the PR minus. So then the same logic, we're basically looking for the change in sign. So it seems it's happening between 7 and 8. So going from a positive number to a negative number. So equal to 0 must be hidden somewhere here. So that means we are focusing on, the range between 7 and 8. So then, yep, 7 and 8. So here we use the same thing as what we did in the first table. So basically, I'm just copy and paste the formula from the top side. So we just save a little bit of time here. So here we zoomed in between 7 and 8. And now when we look at the sign change in sign, we see that this is happening between 7.9 and 7.95. So we for this resolution, as I told you, it's acceptable. So the pH is somewhere between 7.9 and 7.95. So that's accurate enough. So as you saw, the biggest difference between this example and the previous example was basically we added NaPr instead of HPr, and adding a salt of a weak acid compared to just adding the weak acid by itself, we see that the pH changes from 3.95 to 7.95. 9, or somewhere between 3.95 and 4 to a number between 7.9 and 7.95. So a big difference in pH. And then you saw that the controlling factor is this sodium, that is this huge amount of sodium that is directly playing a role in charge balance, which is basically the core of this strategy when finding the pH.
So the third example is asking us the PC-pH diagram for the carbonic acid, something that we did in the previous lecture. But something that we didn't do in the previous lecture was basically evaluating the pH when 10 to the minus 2 molar of carbonic acid is added to the solution. But here we also want to do the calculation on the pH solution in addition to that PC-pH diagram. So similar to what we talked about in the previous lecture, this carbonic acid is a diprotic acid, so it goes through two acid-base reaction. First releasing one proton, so basically we have Ka1, and then releasing the second proton to be fully deprotonated. So plus H plus, and this was Ka2. And in this case, the pKa values are also given. We have Kw term, and in terms of the speciation, we have H plus, OH minus, H2CO3, HCO3 minus, and CO3 2 minus. And since this is added as the acid itself, not a salt of the acid, we basically don't have any other salts, other ions such as sodium or potassium. But if it was added as, for example, sodium carbonate or sodium even bicarbonate, then we have more of those ions here in the speciation and obviously in the charge balance.
So in the third example, we're basically pretty much doing the same thing, but this time the system is a little bit more complicated because first of all, we're adding a biprotic acid. So it's not a monoprotic acid. That means we're dealing with more reactions, we're dealing with more K values, and obviously we're dealing with more alpha values. And the other difference here is that we are not only looking at pH, but also we want to look at the PC-pH diagram. So this example is basically the same as what we talked about in the last example of the previous lecture. So we constructed actually the PC-pH diagram for a carbonic acid system. Based on the rules we had, for example, when you pass a pKa line, the vertical line, the slope goes down by a unit of 1. So those sort of rules that we talked about. But what we didn't talk about in that lecture was finding basically the pH for a biprotic acid system using graphical solution. As I told you, it's a little bit more tricky compared to just a simple monoprotic acid that we define LHS and RHS. And that cross point was relatively easy. So here, the chemical that is added is carbonic acid, H2CO3. And then the total concentration of the molecule was 10 to the minus 2. And the total CO3, or the total carbonate concentration, would be equal to the total concentration of carbonic acid. So this would be equal to the total concentration. Again, dealing with water, 10 to the minus 14. This time we are dealing with a diprotic acid, so we have pKa1. The value is giving at 3.6, 6.3. So the Ka value would be equal to the 10 to the minus the pKa value. And then pKa2 is giving at 10.3. So this would be 10 to the minus the pKa2 value. So the species are also the same logic as we talked about before, always having proton and hydroxide. This time the carbonic acid system is added, so we have H2CO3. We have the first deprotonated version, HCO3 minus, and then the fully deprotonated species, which is CO3 2 minus. So we use this double dash to show this 2 minus. In terms of the charge balance, the positively charged species are just H plus, which would be equal to all the negatively charged species, OH minus, plus HCO3 minus, plus 2 times the concentration of CO3 2 minus, because it's the charge is -2 compared to this, so we have to actually consider this charge value when we talk about the charge balance. This is a diprotic acid, so we're dealing with alpha 0, alpha 1, and alpha 2. And the terms are given here and also in the lecture, the first lecture of acid base. And then this alpha terms are related to the concentration of fully protonated version of the acid all the way to fully deprotonated version. Again, dealing with the same table, 10 to the minus the pH would be the concentration of H plus, OH minus, the Kw term divided by the H plus term, and as a constant. Then the alpha term would be slightly different here. So because of the denominator is a bit bigger, it's for a diprotic acid. So this would be H plus to the power of 2 divided by the denominator. And denominator would be the same for all of them. So I'm going to copy and paste the denominator, plus Ka value times, this would be a constant, times the H plus Ka value times Ka2 value, and both of them are basically a constant. So this denominator, I'm going to copy it and use it. So alpha 1 would be basically Ka times H plus, Ka1 times H plus, and this Ka term is constant, divided by the denominator, and alpha 2 would be Ka times Ka2, Ka1 times Ka2, and then this would be both constant. Again, this control is pretty useful. Alpha 0 plus alpha 1 plus alpha 2 should be equal to 0. And if we expand it, this would be all equal. Sorry, this would be equal to 1. And as we expand it, it's basically satisfying that condition for all of this table. H2CO3 minus, this would be alpha 0 times the total. So alpha 0 times the total, and total has the constant. So this would be the alpha 1 value times the total, and this would be alpha 2 times the total. So the charge balance term, or the left hand side, in this case H plus minus OH minus, the right hand side minus HCO3 minus 2 times, sorry, this was an H23. We had to just consider all the charge species. So this would be HCO3 minus, then minus 2 times the HO3 2 minus. So if we look here, we see that the charge balance is based on this value. The pH is somewhere between 4 and 5. This is where we have a change in the sign. So we just define this to be somewhere between 4 and 5, expanding it, yeah, 4 to 5. And then the same formula, we use it here, just copying and pasting. So now we have a higher resolution. We see that the sign is changing somewhere between 4.15 and 4.2. So it's a pretty high resolution. So the pH of this system that we didn't find using the graphical solution in the previous lecture is basically somewhere between 4.15 and 4.2. So it's accurate to say let's say it's 4.15. So but again, if you want a higher resolution, you can just have the same table, but this time between 4.15 and 4.2, and then go with like a lower steps between this first and the last value. So this is how we calculate pH for a diprotic acid. But the other thing that we can also do, because we have all the values already, is basically constructing a PC-pH diagram. And just to remind you, PC means minus log of C. And C here is all the species. So we have 1, 2, 3, 4, 5 species. So we eventually have 5 lines in PC-pH diagram. H plus is also one of those species. So pH would be basically equal to just the pH that we were dealing with. So this line represents the pH, or the H represented H line in PC-pH. POH would be minus log of the OH from that table. Then H2CO3 would be the same formula, but this time here H2CO3. Minus, forgot the minus. So this would be equal to minus log of HCO3 minus. And this would be just minus log of the last species. And minus, don't forget the minus. So here's basically the same graph as we constructed before, using simple rules that we talked about in the graphical solution lecture. So as long as for pH and POH, this would be like 2 lines with the slope of either 1 or -1. Keep in mind this is a reversed axis on Y. So this line that apparently has like a positive slope, this has actually a negative slope because we're going actually down in the Y-axis. The started with the most protonated version of the acid, H2CO3 here in this case, and then when we hit the first pKa, which is 6.3 in this case, then we start going down with the slope of 1, and then when we hit the second pKa2, then the slope goes 1 more unit down, which is in this case -2. But again, this is the reverse, so we were talking about +1 and +2, the slope of +1 and +2. So this HO3 minus, it hits when it hits the pKa values. This is it just hits one time the pKa lines, so the slope is either 1 or -1. For the CO3 2 minus, it first hit the second pKa, then the slope is -1, then it hits the second pKa line, or in this case, which is pKa1, then the slope goes 1 more unit down. So that was the rule that we used to construct it, like using just back of the envelope calculation, but here this is the exact number with a resolution of 1 unit on the x-axis for this speciation of carbonic acid. So what we did in this example was first finding the pH for a diprotic acid, and then later constructing the PC pH diagram. You also have the data here to construct the alpha versus pH diagram, something that, for example, in the first lecture of acid base, we used that. In this case, we're dealing with the concentration itself, not necessarily the minus log of the conversation, so concentration. So it wouldn't be linear. That would be more. The trend wouldn't be linear if we're dealing with alpha values, which represent the actual concentration, not the log of concentration. Okay, so this would be all the 3 examples for using Microsoft spreadsheet in order to calculate the solution of the pH solution when a monoprotic acid is added. When the second example, when a salt of a monoprotic acid is added. And the third example, when a diprotic acid is added to a solution. As you can guess, there are some other variation that we can use this. For example, when a salt of a diprotic acid is added, or dealing with a triprotic acid system, such as phosphoric acid. But the logic would be the same, going for the original table, the first table, and then finding that range, finding the 2 numbers that this charge balance related term is switching between negative and positive value, and then focusing or zooming in that range in order to increase the resolution of your calculation.
So in the second part of the lecture, we're going to talk about Visual MINTEQ for acid-base speciation, and specifically focusing on calculation of pH, solution pH, and also constructing a PC pH diagram. This software is free, and it's a very powerful tool for a wide range of environmental applications, from different phases, for example, gas phases, liquid phase, their contact, the solid phase. But in this particular lecture, we're focusing on using this application for acid-base systems. So within acid-base framework, this computational algorithm, including those that are implemented in Visual MINTEQ, can be used for 2 purposes. So in the first purpose, the first goal is that we know the concentration of all chemicals that we added to the solution, and then what we're looking for is the final concentration or the final composition at equilibrium. So we know what we added and we know how much we added. Then our job would be to calculate, or the application job, the algorithm job would be to calculate how much we have for each species at the equilibrium. So that's the first goal. And the second goal would be, we know one of the final condition. For example, we know the final pH of a solution. Then the question is how much, for example, of that particular weak acid with, for example, that known pKa, we need to add to the solution in order to satisfy that initial condition, or in order to get to that pH. For example, how much HPR we need to add to a solution to get to the pH of 4. So that's the second category that we can approach, that we can use this software for. So in this lecture, we're just focusing on the first category. Basically know the composition of all the inputs, and then we're predicting what's going to happen for the output. And when we look at the flow chart, we see behind the scene, this is what's happening in all the computational algorithm, including what is happening in Visual MINTEQ. So this is, again, behind the scene, what is happening. We have the actual input. They have this logical flow chart in order to get eventually to a result that is acceptable based on the criteria we define. And it's basically just a very logical path for any calculation on the speciation. So it's just to show you what's happening behind the scene. So in this lecture, we're going to use Visual MINTEQ for two examples. So in the first example, we're adding acetic acid to water, and we just want to know what's the pH of that solution. So acetic acid is a weak acid. If we look at the molecule, we see that there's like and this is an organic molecule. So we note this as AC and H part. So we abbreviate it normally as HAC. But when you look at the software, normally it is abbreviated as H acetate. So H acetate is basically the same as HAC. It dissociate to AC minus plus H plus with the Ka value. And then in terms of the species, we're expecting H plus OH minus, HAC, and AC minus. So basically what we need to enter for the software, as you'll see, is just the total concentration value of HAC. So the total concentration is basically equal to the total concentration of H plus that we're adding, and is equal to the total concentration of AC minus that we're adding to the system, because one molecule of HAC produces one molecule or 1 mole of H plus and 1 mole of AC minus. So we need that sort of information to calculate the pH using Visual MINTEQ.
So before using Visual MINTEQ to solve the examples, I'm going to walk you through the software itself, some of the useful tabs that we're going to use, and also the platform itself. So the software can be downloaded for free. Just Google Visual MINTEQ download, and this is just available for Windows. It's unfortunately not available for Mac users. This is actually a freeware, so it's pretty easy and straightforward to install it. So let's assume you have the software on your computer. This is basically the actual design, the actual user interface of the software. Just pretty standard in terms of the tabs and also some inputs that we're going to use for this lecture. So starting from the tabs, as you see, this is pretty comprehensive. And it basically, it's pretty useful not only for this chapter, which is around acid-base system, but it's also useful for other part of the chapter. For example, when we deal with the gas equilibrium, or chapter 4, for example, when we talk about redox chemistry. So this software is in general very useful for a wide range of applications within environmental chemistry platform. So very, very useful. But for this lecture, we are focusing on just the basics of acid-base solutions, and in order to find pH or construct a PC pH diagram. So to just walk you through the tabs, just basically a file tab, pretty standard for other software, so nothing to say about it. The second one is parameters. So you see some technical terms here. For example, alkalinity is something that we're going to talk about in this chapter later on. So this is how to specify some parameters related to that particular lecture if you're going to use the software for that. Or PEEH diagram, something that we're going to talk about at the end of this course in chapter 4. But then this tab in general is basically talking about the parameters. But what is important here, it's this various default setting, which is basically a default for a wide range of application, no matter where you're doing activity, or whether you're doing acid base or a redox. So this is something that we're going to use also for this lecture. So if we look at this tab, you see that there are some important parameters that you can play with. But the most important one that we're going to use is basically the method of activity correction. So if you remember in the class, we talked about a wide range of theoretical models that we can estimate the activity coefficient in order to calculate the activity values based on the concentration. So it is already built in the Davis, the Biohockle and SIT actually in this platform, in this software. So it just made our life much more easier by just picking the actual theory, and then based on that, based on our choice, the software does all the following calculations. So if you remember in Davis equation, we had this B parameter, which was based on, like, let's say, temperature and some other features, but we consider that as 0.3, so 0.3. So this is the same also here. And if we go for the Biohockle, it's just basically the related parameters for the Biohockle, which is not asking us anymore. So for SIT also, it was more involved, as you remember. But the range of ionic strength dictates the model that is suitable, and most of the time Davis equation is pretty accurate to estimate the activity coefficient. So I just wanted to show you that you can basically change this in the software. So the activity model that you're picking can be changed here. And the rest is basically just talking about some technical databases that are already installed when you install the actual software. So if we choose Davis, then you see the activity model that was chosen is Davis. So let's say if we change it to the Biohockle, just make sure always that it's also responding. So let's go back to the Davis equation. So the next tab that is important for our job here, these are, like I told you, very important for the following lectures, but for this lecture, this sweep function. So this is basically, technically speaking, any sweep function is basically like a loop when you're dealing with a programming language. So you say just sweep your variable, let's say your solution pH, from the initial value to the final value using this incremental values between. So this just basically does the calculation for each individual value and give you the output as a matrix of your variable versus the output. So we're going to use this when we're constructing the PCPH diagram. And this is again based on the database management. If you're going to use your modified database for thermodynamic calculation, then you can just change it here in this tab. But we're not going to change the database. So we just use the one that came with the software, which is actually pretty comprehensive. And the last one is basically the help tab, pretty useful. The user guide is just a PDF file that gives you tons of information with some good examples. And this interactive help file is actually helping you to have it's clickable. So you can basically go, for example, to redox problem and gain some basic information about the type of output that you're going to get from the software. So that's about the tab. And if we go down, we see that this is just pretty basic in terms of the user, the interface design. Just this is not clickable, just a picture. But what matters is these tabs that we can basically use to define the input. So starting from the right side, we talked about this activity, basically the model that is used. Then it's just asking us what unit of concentration we're going to use throughout this calculation. So most of the time in class, we talked about molarity. So basically mole per liter, the total liter. But then if you go down, there's no molarity. But as you know, molarity and molality is pretty similar. So molality is basically just a slightly different definition, but in terms of the quantitative values is pretty similar to molarity. So we stick to this molality But you can also do, for example, milligram per liter, and then convert your molarity values to milligram per liter. But molality would be accurate enough for us. The temperature, one of the operational parameters that is as a default, is set to 25 degrees C. This is basically Celsius. So this is about the operational window, operational parameters, how we define individual species. Then if we go on the left side, this is basically one of the key aspects of how we approach the problem. So, for example, this says how do we want to calculate the pH? It could be calculated from mass balance, or it could be calculated from mass and charge balance. So you'll see that later, mass balance by itself, so the default, which is on mass balance, it's pretty accurate. But to make it more accurate, you can just rely on mass and charge balance. So that means it takes more time to do the calculation because the number of iteration would be higher. You'll see that in one of the examples. So these are category 1 of what we talked about in the lecture. Category 1 is basically we tell the software how much initial we have, and we ask the software to calculate the equilibrium composition, or the equilibrium speciation, or the equilibrium concentration of individual species. So that's how it works. So in that case, pH has to be calculated. pH of equilibrium has to be calculated based on the input that we are giving the system. The second category was one parameter is fixed. For example, pH is fixed. Then the software will calculate how much of, for example, propionic acid we need to add to get to that pH. So we're not covering that in this lecture. So we are basically what we are doing is giving the software the total initial value, and this is what we have initially. Just give us the final equilibrium composition, including the pH. So the pH calculated from the mass balance, ionic strength, so obviously it has to be calculated, but then if it's fixed at, again, is the second scenario. And then we can add individual components. So this is the key here. Again, we can have the total concentration at the beginning, molal. Let's say if we change this to millimolal, let's change to millimolar, but let's keep it at molal. Or the second scenario, that this is a fixed activity at equilibrium. So if we select this would be the second category, which is not a part of this lecture. So we stick to this total concentration, something that we used throughout the previous lecture. So this is the total concentration of, let's say, Cl, when it's in the form of HCl and Cl minus. So that's the same variable. Again, the same variable that we have in the denominator of the alpha notation. So, and this is the component names. There's a list, and then we can have the total concentration, and then adding to the list. So we need to actually click on this every time we add a component. So this is not a molecule, but it's basically a component, or it's a species that we are introducing to the system. Then we can view the list, what we already added. It can be always reset. So whatever you add, you want to go back to clean everything, to just reset it. And then when you're done with putting all the species, then you basically run MINTEQ in order to calculate for speciation to give you the equilibrium based on the first category, based on the category that we calculate everything based on the initial total concentration. So that's all about the software itself. So now let's focus on example 1. Example 1, or the first example of MINTEQ, which in the lecture is example 4 actually. So in this example, we're adding acetic acid. So when we look at the acetic acid composition, it's an organic molecule, it's an organic component. So we need to activate this. So if it wasn't activated, you see there's no organic here. But then when you activate it, you see tons of organic like this one, benzonate, or the other species. So here we're adding a acetic acid. So the species, the components that we're adding, it's obviously the acetate and also proton. And we know the total concentration. And for one molecule of acetic acid, we're introducing one molecule of acetate and one molecule of proton. So the ratio would be 1. So first we have acetate, so acetate minus 1, and the total concentration is equal to the total concentration of the acetic acid that was introduced, so 2 10 to the minus 3. So we use this E sign for this program. The same was for Excel also. So acetate 10 to the minus 3, add to the list. Then we have also proton. The total proton that was added because of acetic acid was also the same as 2 10 to the minus 3, add to the list. So now we're done with the species that was added to the list, but these are not the final species because we know that we just added acetic acid. We didn't specify all the possible species. For example, hydroxide, we didn't specify that. And that's the job for the software, to give us the speciation, what species we have, and what are the final concentration. So let's look at the list of the input. When we look at the list, we add 2 10 to the minus 3 proton, 2 10 to the minus 3 acetate. And this is, it gives us a good information about, like, because of the species that we already entered, then we have important information about the species. For example, H acetate, or this is acetic acid, the way, as I mentioned in the example, this is the way that the software use the abbreviation for acetic acid, H acetate, instead of HAC that we use in the class normally. So it says H acetate is involved in a reaction that involves acetate and proton. So this is basically the reaction. This is the stoichiometric coefficient. So this is the dissociation of acetic acid. So that's one of the reaction that is going to happen in this system. And then the log K, so basically minus the pKa of this system, would be 4.757. And just keep in mind, the way this reaction is written is not necessarily giving us Ka. Sometimes it's giving us 1 over Ka, because this stoichiometric coefficient, we have to be careful about the negative and positive sign. So the pKa, if you remember, so we use the pKa for this acid was 4.8 roughly. So this is the exact value. So that means the reaction is written in the opposite way. And then we also have the second reaction, which is basically water dissociation. Water going to proton and hydroxide. And the log K, which is Kw in this case, is around 14. So this minus is again because we define the reaction in opposite way. So that assuming Kw at 25 degrees C is 14 is pretty accurate. You see that this is 13.997. Also, the other important information that we have is delta H of the reaction. So this is very important. You saw that Van 't Hoff equation. Delta H was needed to correct for K values for different temperatures. So this software, based on the database that was defined, is already giving us the delta H of the reaction that we can directly adapt in order to calculate K value for different temperatures. But if you're defining the temperature in the software, like here, this K value will be automatically updated, so no worry about that. But this is a good information that you can get from the software for a given reaction. So this was general information about what you already inherit based on the concentration, so the species information, the type of reaction that you're going to have when you solve for speciation. So now I guess we're ready to run MINTEQ. So if we run this, this would take less than a hundredth of a second, and the number of iterations was 5. Just before we go through this table, I just want to change this to the mass and charge balance and then run the same thing. The number of iteration was 1000. So that's what I was telling you about. Mass balance is enough. And then it will give us the same value. Let's just say this is the pH of solution, 3.749. And then if we go back with the lower number of iteration, this would be again the same, 3.749, but way lower. So let's start with the output. So this is the result of the software. So obviously it's giving us the pH of the solution, so 3.749, pretty accurate. And then the ionic strength based on the solution that we have the total concentration. Then these are the sum of cation, sum of anion, and this is the charge difference. So here is charge balance. So this is basically the core of calculation, that iteration, that the flow chart that we talked about in the lecture. So now this is basically the main table. It's giving us the concentration of individual species, acetate, proton, acetic acid, and then hydroxide. And then not only concentration, but also the activity and log of the activity. And obviously we can quickly calculate the activity coefficient here. Let's just actually do that for one of the species. Activity coefficient of, let's say, acetate. So that's both of them 10 to the minus 4, so we just ignore that. So this would be 1.784 divided by 1.8120. So the activity coefficient is 98. So the solution, the ionic strength is pretty low, so it makes sense that this is very similar to an ideal solution which has the activity coefficient of 1. So pretty accurate in terms of if we want to go with the concentration of this system would be the pH that we're calculating eventually, either using algebra or graphs, would be similar to what the software would give us based on the activity values. So this is basically the core. So this is the speciation, or the activity or concentration of all the species at equilibrium for the acetic acid solution. We can obviously print it to Excel. This would be very straightforward. If we just click it, then you have an Excel file generated immediately for the speciation, all the information that you have in the information that you have on this box. Then you can have like a speciation distribution. For example, the acetate, if we consider the total acetate that was introduced, 90% of it is in the form of acetic acid, and just 9% of it is in the form of acetate. And this makes sense because acetic acid pKa was around 4 point something, so this is a weak acid. And dissociation of weak acid, one of the assumptions we had to simplify the solution in one of the lecture was that for strong acid, they dissociate almost completely, and for weak acid, most of them won't dissociate. So the major part of it would be the protonated version of the acid, which is in this case a H acetate. If this was HCl, this would be opposite. Most of it would be in the form of Cl minus rather than HCl. This can be again printed to Excel if you need it. The other one is the saturation index, to just whether we're passing any saturation of any salt, so that would precipitate or not. In this case, nothing is precipitating. We'll see that later in one of the lecture, that sometimes we're dealing with precipitation, equilibrium with precipitation. Then you see that some of them are basically precipitating, but not in this case. The other thing is just sort of a mass distribution of again the species, that the ions that we're dealing with in the solution, the total dissolved, the percentage of dissolved, the percentage of sorbed, the percentage of like precipitated, So it's sort of a good information, complementary information for your system. But in this case, because the system is pretty simple and straightforward, this would be all 100% dissolved rather than, let's say, precipitated. So that's all about example one. Basically, we calculated the pH and the speciation and the concentration at the equilibrium for all the species. So pretty straightforward, pretty easy to enter the values and pretty easy to read and look at the values and export the values later to an Excel file. So that's all about the example one.
So the last example is basically asking us to construct the PC-pH plot for carbonic acid and also calculate the solution pH for this weak acid when it's added, when 10 to the minus 2 molar of this is added to water. So again, the reaction would be, the reaction that are involved would be the same as what we talked about in example 3. So basically it's a diprotic acid releasing 2 proton, but step by step we can define the K value. So Ka1, Ka2. And so what we know is that 1 mole of H2CO3 produce 1 mole of CO3 2 minus, and then 2 mole of H plus. So this is the input of the software. So the software would solve for all the species, but this we need these values, this ratio for the input of the software. So basically, this is not the input. Let's just put it this way: that this ratio means since we have 10 to the minus 2 molar of H2CO3, then we have 10 to the minus 2 molar total CO3 2 minus we add into the system, and 2 10 to the minus 2 molar H plus we are adding to the system, and we want to calculate the final pH and all the speciation. So this would be the input of the software based on the molar ratio that we have for this particular molecule. So now we're going to use the software in order to calculate the solution pH and also construct the PC pH diagram.
So now let's focus on example 2. Again, example 2 of the Visual MINTEQ part of the lecture, which is example 5 actually. So example 5 is asking us to have to calculate the pH for carbonic acid solution, and also have the PC pH diagram for carbonic acid. So the first thing, we need to reset the database. So if we look right now at the database, we see that there's acetate. So we don't want that in our system anymore. So we just need to reset it. So just to make sure acetate is gone from the list. So we just need to enter the species again. So the same thing for, we're going to calculate the pH and ionic strength. We are dealing with molality at 25 degrees C. I mean, we don't have any organic component, so it's just bicarbonate system. So we don't need to activate this. So we're adding carbonic acid H2CO3 minus. H2CO3. So this is the molecule. So we know the concentration, the total concentration of carbonic acid. So for one carbonic acid, we have one CO3 2 minus. So the concentration of CO2 3 minus, CO3 2 minus, would be the same as the concentration of the carbonic acid. So this would be 1 10 to the minus 2, or 10 to the minus 2, added to the list. So the second species that we're introducing by adding carbonic acid basically is proton But then the ratio of proton and carbonic acid is we're introducing 2 moles of proton per 1 mole of carbonic acid because it's H2CO3. So then proton concentration would be twice as the total concentration of carbonic acid. Add to the list. Let's view the list and let's look at the reaction. So here you see that you have 2 reactions here. This is as I told you, this is a biprotic acid system. It's not monoprotic. And obviously we have also water dissociation, the same thing as we had before in terms of the value and in terms of the delta H value. So here is the first dissociation of carbonic acid, and then this is the second dissociation. But if you remember in the Excel examples, one of the pKa was around 10.3, the other one was 6.3. But then when we look at the first reaction, it's written in a way that has 2 proton. That means this is a combination of both first and the second step. And we know that for the overall reaction, which is a combination of the first and the second step for a biprotic reaction, would be the pKa would be the sum of 2 pKa's. One of them is 10, the overall is 16. So the first one was 6 point, in this case 6.3. Again, the same exact value that we had and we used for the Excel spreadsheet. So just don't worry about this number. This is 16 because it's a combination. And obviously delta HR is also a combination of the 2 reactions. So this was just written in a way that is both reactions together. Okay, I think everything is good to go. We can just stick with Davis in terms of the activity coefficient and just run the MINTEQ solution. So then the number of iteration, 8, not bad. But then if we go back, making a discharge and balance, this would be 46. In this case, it wasn't bad. So let's just stick with just the mass balance. So the charge difference is very, very small. So that means the accuracy of the solution is pretty high. The pH of the solution is 4.177, and the ionic strength is around 10 to the minus 5. But we did the same exact example using this Excel spreadsheet, and what we got from that Excel file was, first in this table we figure out the pH is somewhere between 4 and 5, where we have the change in the sign, and then when we zoomed in on between 4 and 5, we figure out that pH is somewhere between 4.15 and 4.2. So now software is telling us that it's pretty accurate. The Excel spreadsheet was pretty accurate. So 4.18 is obviously between 4.15 and 4.2. So just it shows the Excel spreadsheet was also pretty accurate. And if we do it basically using algebra and or graphical solution, this would be pretty much around this 4.1, 4.2. So pretty accurate. Then we go back to speciation. So we see now all the species, CO3 2 minus, H plus, H2CO3, HCO3 minus, and OH minus. And then you see that the concentrations are given. But now let's just compare it with the values of concentration that we were getting for from the Excel file. So here let's assume the pH was 4.15. So 4.15 is close enough to the actual pH given by the software. So here the Excel file predicted that the concentration of H2CO3 is 9.93, 10 to the minus 3. And if we go here, is 9.9329, 10 to the minus 3. So very, very close. Or the HCO3 minus bicarbonate is 7.03, 10 to the minus 5. And here is 6.7, 10 to the minus 5. Again, very close to the predicted value by the Excel file. And the same thing for bicarbonate. So the same thing, we have the species distribution is 99% in the form of H2CO3 and less than 1% bicarbonate and very negligible amount of carbonate. And the saturation, nothing is precipitating, and then the equilibrium mass balance is just giving us that it's all dissolved. So that's about the pH part of the calculation. So we calculated pH for carbonic acid when 10 to the minus 2 molar of carbonic acid is added to water. But then the second thing is we need to also construct the PC pH diagram, like what we did in Excel file. And as I told you at the beginning of the this part of the lecture, I told you we can just have like this sweep function, just sweeping one variable and just repeat the calculation over and over in order to have this eventually this D diagram of the sweep variable on the x-axis and the output on the y-axis. So let's just work on the sweep. So we want to just change one variable here. Sweep one parameter. Then the number of problems, we want to do it 14 times. And we want to do it on pH, the sweep component. Later on, for one of the lectures in the fourth chapter, we, for example, do on the PE. But here we just do it on the pH. The starting value is 0, and the increment between values is 1. So we go from 0 14 times, and every time we increase 1. So this is how we enter the values in order to go between 0 and 14, the pH of 0 and 14, and with incremental values of 1. Then the output, what we want to calculate is basically the proton, and then we want to have the log of concentration. So this is not exactly PC, this is a minus PC, so this is the log of concentration. So the curve should be the same, but this time it's the values are negative. So the log of concentration is negative of P of the concentration. So, but the magnitude and the shape should be the same. So we do it for proton, we add it for proton, we add it for hydroxide, and then we add it for the carbonate species, H2CO3, then HCO3 minus, and then CO3 2 minus. So we should have 5 lines, 5 each line for each species, all log concentration, and then all as a function of pH. So save and back. Again, we already entered the values, the total concentration. We just need to run. But now this time, it's a little bit different. The table is actually the same, but here you have the number of iteration that you selected, starting from point 1 to point 14. So the first point, the 14th point. And in all the points, it's actually predicting, it's setting the pH at these values and then changing the calculating for the rest. So as you see, the numbers in the table is changing. Now we have the same information. The first 3 tabs are the same, but now we get this select sweep result. We already told the software what is the input, the variable, and what outputs we're looking for. Log concentration for 5 species. So if you look at that, it's basically giving us for the pH between 0 and this gave us the pH of 14. So we had to make this point actually 15 to give us the whole range of pH. So just going back, this would be 15. Run MINTEQ, and then the pH between 0 all the way to 14, and then we have the log of concentration for H plus, OH minus, exact same thing that we had for uh, when we did the calculation with Excel. And then they all ran successfully based on the calculation. The flow chart for calculation work well for all the species at all different conditions. Now we can just print it to Excel, the same thing we did. And the new Excel file looks like this. So let's just compare the graph we're having here, or the graph that was just the data was adapted from the software. So let's see how this looks like. This would be something like this. As you see, this is basically the same graph as what we got using the Excel file. Let's just make it a little bit cleaner from -14. So this would be to 0. And then the values are between here 0 and 14 on the x-axis as well. So as you see, this graph is exactly the same as the graph we had with the Excel file. Obviously, this is more beautiful, but this one, the same trend, the same slopes. For example, here going from 1, passing another pKa to -2, or -1 to -2. But just keep in mind, this time these values are negative because we didn't use p function, rather we just did the exact log concentration rather than minus log of the concentration. And it would be all the same for all the species. This line is OH, the same as the previous case. This should be the bicarbonate, the carbonic acid, and carbonate. So basically getting the same thing, the same information from the software as we did for the Excel. So that shows how useful the software is to not only calculate and estimate the pH, but also be able to sweep for one of the variables and construct so many useful graphs which can be used for which provides the useful information for environmental systems. So that's all about the last example, example 5 in the lecture. So just to wrap up, this software is pretty useful, pretty intuitive. We can have two approaches. One is to give the total concentration of individual species one by one to the system and ask what is the final concentration at equilibrium, and the speciation, including what's the final pH. That's one thing we can get from this software. Or we can have like a fixed value either for pH or the activity of one of the species, and then ask the software what should be the condition to get to that fixed value of that parameter that we define. For example, what should be the concentration of carbonic acid if we want a solution with a pH of, let's say, 5. So that sort of information. If we actually fix it, then it's ask us what is the fixed value of this parameter, which is pH in this case. Then just make sure you're adding to the list every time you want to go for another example, another scenario to reset it. Always check your list, then see whether all the species are already defined, and after that just run and get the important information from the software. This activity can be changed. The software is flexible in terms of the type of database that is used or the type of model that are implemented for the calculation of species and the equilibrium calculation. You can use it for other chapters of the course, such as redox, gas, or outside of this course, such as the adsorption and solid phase parameters. So in all, this is a pretty useful free software for a wide range of environmental applications.
So to wrap up, in this lecture, we learned how to develop a Microsoft Excel for calculation of the pH for example, we use that LHS minus RHS term in order to, based on the charge balance, and see when, for example, the sign is changing. Then we were just zooming in this range of pH in order to increase the resolution of the calculation. And we also use the same table in order to basically construct a PC-pH diagram. And for the Visual MINTEQ, we basically had the platform that the input was the total concentration. We show that we can use, basically, we can change the activity coefficient model. We can also sweep some variables that we could basically construct the PC-pH diagram eventually. And then we saw that there's like a very good agreement between the result we got from Excel and also the result that we got from the software. So if you're interested to know more about this stuff, just I refer you to the book. The Excel file was adapted from chapter 5, and the software section of the lecture was adapted from chapter 7. And in the next lecture, we're going to talk about titrations. Thank you.